This is the first in a series of videos on models in epidemiology and biostatistics. My name is Gordon Hilton Fick, and this is session number 1. It is my intention to provide an introduction to the use of models in epidemiology and biostatistics. I'm assuming that anyone that's watching these videos has had a strong graduate course in statistics. It is anticipated then that the course would include material comparable with the fine textbook by Moore, McCabe, and Craig, An Introduction to the Practice of Statistics. But there's many other ways to gain the material. The key parts are a clear understanding of a test of significance, a clear understanding of a confidence interval, and some of the basics, including, say, chi-squared tests and t-tests. Nothing to do with statistical models of any kind are assumed for this series of videos. And in this first session, what we're going to do is set up some of the preliminaries that are necessary before we can get to the heart of how to construct models in epidemiology and biostatistics. So you can see we've got a collection of important issues that are listed on this first slide. Many of them will be expanded considerably. We're going to have an outcome that is success or failure. We're going to describe that outcome in terms of probability or odds. That will lead us to various choices as to how we represent these probabilities or odds. We will also provide a very basic start to understanding of crucial issues in epidemiology, including modification and confounding. All of the sessions that I'm going to be doing here are built around the fact that we need to construct models that provide us with the ability to interpret the models and the implications of the models. So we're going to see that there's a wide range of issues involved. Using the statistical models will give us a lot of material. The challenge will be, do we need the elaborate things that are a part of statistical modeling? Or can we provide, in the project that you're working on, with all that you need with comparatively simple things? There's a lot of tough issues here, and we'll try and cover them all in these sessions. I thought I would set up an illustration to provide the background and context for the main topics that are going to be discussed here. So we're going to imagine that we have patients that have agreed to be a part of a study post-surgery. And we will imagine that the outcome that is of interest for our purposes is just a measure of success. Further, all of the patients received one of two different pre-operative treatments. So we will have the outcome being success, failure, and then the treatment being the characteristic that is, if I may, it is going to be the characteristic we would like to understand and the impact that such a treatment has on the success or failure as measured. Inevitably, then, we're going to have some notation. In epidemiology and biostatistics, there's a fair bit of symbolism, but it will be important as you move forward to use the descriptions of these symbols rather than just the symbols themselves. So we have the two preoperative treatments, T1 or T2. We're going to keep it generic, so we'll just refer to pretreatment number 1 and pretreatment number 2, and the outcome, success or failure, S or F. Inevitably, then, we have the population characteristic that we wish to understand. And we can describe it in terms of the probability of success. Now, what we're going to have is that this probability may depend on the pretreatment. Inevitably, then, we wish to consider conditional probabilities. The probability of success given pretreatment, which has the symbolism that's shown there. The vertical bar is not spoken, it's just how you describe given. So the probability of success given pretreatment 1 and the probability of success given pretreatment 2. And we will find that sometimes we'll abbreviate these even more as P sub 1 and P sub 2. The way in which we write them, we'll use simpler terms, but the descriptions are the crucial thing. They are probabilities of success given the treatment. So in epidemiology and biostatistics, we have risks. Sometimes probabilities are called risks. It is often seen in health research that we refer to risk rather than probability when the outcome is something negative, like mortality. For example, the probability of death is often called the risk of death. But we wouldn't speak of the risk of survival. We would then have the probability of survival. We have probabilities that are sometimes called rates. Now, the language here can get a little bit confusing at times. We speak of success rates, failure rates, mortality rates, remission rates, and the outcome. This rate could be a positive or a negative characteristic. Obviously, success rates typically are the good guys. Perhaps the most basic characteristic that one can construct is the rate difference, which is the difference between the probability of success with pretreatment 1 minus the probability of success given pretreatment 2. There's lots of ways in which one can write the risk difference. So, for example, if we were to have that the risk difference was 0.2, then we could say the success rate for pretreatment 1 is 0.2 more than with pretreatment 2. We can also have ratios. We can have rate ratios, where we take the ratio of the probability of success with pretreatment 1 and divide it by the probability of success with pretreatment 2. Inevitably, then, we have a way to describe such a ratio. For example, if the rate ratio were to be 1.4, then we could say that the success rate for pretreatment 1 is 1.4 times the success rate for pretreatment 2. So we have our first landmine, I guess, when it comes to the discussion of ratios and differences. And we have to be careful. And there's language that you will see in your literature where it can be unclear whether or not one is speaking about a success rate in one group and a success rate in another group, and are they doing so in relative terms or in absolute terms? And that's described with the relationships shown at the bottom of this slide. Now, when the outcome is something negative, or it's being posed in terms of something negative, like a failure rate, mortality rate, then we can have, instead of a rate difference, we can have a risk difference. Similarly, we can have a risk ratio. And those are the terms and how they're written. So we have ratios of probabilities, rates, and risk and health. One might argue that for clarity, referring to these ratios as probability ratios would be the clearest, but this isn't often seen in the literature. But we should be careful to speak of risk when it is something negative. Sometimes you will see, for example, risk ratios when the outcome is something negative, and one will sometimes see the term health ratio when the outcome is something positive, like a success rate. So when you see something described as a rate ratio, it should be that one means a ratio of probabilities. Because we now come to our next issue, and that is odds, which I hope you've all had some exposure to in your previous courses or your previous study of probability and statistics. Inevitably then, an odds is a ratio of a probability divided by 1 minus the probability. And we can have conditional odds just like we have conditional probabilities. We can also have, for example, the odds of disease or the odds of failure. And it turns out that in some contexts which we'll be describing, we can also have the odds of exposure. For example, it might be that pretreatment 1 is thought to be inferior to pretreatment 2, and so the odds of being exposed might be the issue, the odds of someone receiving pretreatment 1. Now, this is a little bit confusing, and we'll come back to this, and I'll try to make it clear if I can. So odds are seen very often in epidemiology and biostatistics. It's very important to keep in mind that odds are not probabilities. For example, if we have a probability of 2/3, the odds is 2. We have a probability of 4/5, the odds is 4. Well, clearly odds can be greater than 1. And in any case, odds and probability can be very different. Now, they can be close, but they'll never be identically the same. Now, even when they are close, you will see some authors that will interchange the language referring to odds as probabilities. I don't recommend you do that, because there are so many instances in which, even though an odds and a probability can be close by some measure, how we end up modeling odds or modeling probability can be very different. They're very different issues. Very, very different. It turns out we can display the relationship between odds and probability. And here is a graph. You might notice that in both scales here I'm showing both the vertical and the horizontal scale are linear. And you can see that odds and probabilities can be close when the probability and or the odds are near zero, but they can be different. It's of interest. Now we have our first use of logarithms. If we display odds on a logarithmic scale, we can see we get a very different image. I'll be coming back to how we wish to use such an image in the arguably most widely seen model in epidemiology and biostatistics, and that is the so-called logistic regression. And we'll be coming back to this image. Notice here where I'm plotting probability on the horizontal scale and the log of the odds on the vertical scale. We can have, just like we have rate ratios, we can have odds ratios. So we can have, for example, the odds of success with pretreatment 1 divided by the odds of success with pretreatment 2. So we would then have, for example, if an odds ratio were to be presumed for a moment to be equal to 3, then we'd say the odds of success with pretreatment 1 is 3 times the odds of success with pretreatment 2. Now, we don't say risk here, or likely, or probability when you mean odds. It can really be confusing, and it's not recommended. Now we come to perhaps the most interesting of characteristics, and that is the logarithm of the odds. The magic of logarithms. This is maybe one of the very first issues where you're going to have to perhaps go back to previous courses you've taken in math and review logarithms. We won't be actually computing directly logarithms very much. We'll be using software to do that, or calculators to do that. More to the point, though, we'll be using properties of logarithms that help us as we move forward. It turns out that the logarithm of an odds ratio is the difference between two log odds. And the log odds is called a logit. Aha. Now we can also take the logarithm of a rate ratio. We could take the logarithm of a rate ratio, and then we get the log of the probability of success with pretreatment 1 minus the log the probability of success pretreatment 2. So the logarithm of a rate ratio is a difference between two log rates. Also very crucial for us will be that if a ratio is 1, the logarithm is 0. The logarithm is 0 of that ratio is 0. The ratio is less than 1, then the logarithm will be negative. And if the ratio is greater than 1, then the logarithm will be positive. All important steps for sure as we move forward in trying to understand how the log odds, or the logit, comes into our work in epidemiology and biostatistics. Okay. With that set up, let's take a look at a study. Actually, this illustration comes from a very fine book by Jim Kalbflesh that was published in the 1970s, and I am adapting the example from Jim's book from volume 2, and there's the page reference if you'd like to acquire this book. It's a very, very fine book, probability and statistics. So let's take this little 2x2 table. Notice we'll put the outcomes, the possible outcomes are the rows, And the possible exposures are the columns. So we have two outcomes. There are two rows, success and failure, and we have two exposures. We have those exposed to or receiving pretreatment 1 and those receiving pretreatment 2. This is fairly standard, putting the outcome as the rows and the explanatory variable as the columns. And we'll be coming back to this. But from this simple table, we can compute estimates of the probabilities that we've described earlier. Now, here's where we have to be clear. We're going to be constructing some proportions here, some ratios of actual numbers. Here's where it is important to use different symbols for the estimates. In this illustration, we'll be using hats for the estimates. So P1 hat is this 195 over 1100, and P2 hat is 505 over 1100. Those are estimates of the unknown probabilities. The probabilities are never directly known to us in epidemiology and almost all of biostatistics. So then we have estimates of those probabilities. To what extent are they any good is part of our exploration. Maybe the very first issue is, well, those two estimates are different. Does that mean we can, with any sense of surety, conclude that the probabilities are different? Maybe more crucially, as we'll see later, is it now given that the probabilities are meaningfully different? And what do we mean by that? So, keeping in mind, in epidemiology and biostatistics, it's important to use different symbols for the population characteristics, here are the probabilities, and the sample characteristics or characteristics computed from the data. So when we have an estimate, we need an estimate of what? We have the estimate in this case having a hat. We will see, though, in lots of illustrations as we move forward, that the estimates are used, or will be using the Latin equivalent of the Greek letters that are used for the population characteristics. So, for example, we will see that we will want to use the Greek letter beta quite a bit, or alpha, or gamma. But what we'll have is the estimate then, in some instances, will be the Latin equivalent. So if we have a population characteristic that we wish to call beta, then the Latin equivalent would just be the letter B. If we have the Greek letter alpha, then the Latin equivalent would be the letter A. And so on. So we know that the estimates then are not the same as the probabilities. And the reason they're not the same can be because of error and other more elaborate things. Perhaps in your introductory course in probability and statistics, you talked about error. Maybe you saw some illustrations with card games. We don't know the probabilities except in these simple examples with card games. They will be the unknowns almost all the time. And they're unknown because, well, we don't have a census. We may have a large number of participants in our study. In this illustration, we had 2,200 patients. But we know that's not all the patients. That we'd like to make a statement that applies to not just those 2,200 patients, but to the population of all comparable patients, perhaps. So the samples provide us with estimates of population characteristics. And we're going to distinguish between the populations and the samples. Very, very crucial here. What have we got then? We have estimates of the probabilities, so we have estimates of the characteristics that we've computed earlier. For example, we have an estimate of the rate difference. We have an estimate of the rate ratio, and they're given as illustrated here. To what extent that estimate minus 0.2818 is close to the actual population characteristic, the rate difference, is something we would like to study. Same thing with odds ratios. We can construct estimates of odds of success. We can construct estimates of odds success in both groups, both pretreatment groups, and then construct an odds ratio, literally the ratio of the estimates of the odds. And we get a number. Here, 0.2539. Okay. What of any merit is that number? In epidemiology in particular, and in biostatistics generally, a more crucial issue is bias. Arguably, at times it can be much more challenging for the researcher that there's bias. Sampling error is something that's comparatively easy to handle. But bias, oh boy, that can be tough. That can be a very tough one. We will see that one of the forms of bias that really can be a challenge for the epidemiologist or the biostatistician is one that has many different names. The oldest, though, might be Simpson's paradox. So let's now return to the surgery example again and make life more complicated. So what I started with for you was an outcome, success, failure, an exposure that was pretreatment 1 or pretreatment 2, and now we're going to add an additional variable. And that is the type of surgery that the patient received. And for our illustration here, we'll suppose that there were 2 types of surgery. And we'll keep it generic. We'll refer to the surgery types as A1 and A2. Well, it turns out then that for each individual, each of the 2,200 participants in the study, we have not only which pretreatment they received, but which surgery they received. And then we will then have their success or failure as judged from the questionnaire they completed. Now let's suppose the data from this study looks like this shown in this display. We have 2 2x2 tables. We have the 2x2 table for surgery group 1 and the 2x2 table for surgery group A2. And you can see right away, well, they're not the same. Those tables are not the same. Okay, but how are they different? Let's see if we can get our head around this. Now we have estimates of the rates, the rate differences, the rate ratios, the odds and the odds ratios, but we have them for both surgery groups, for surgery group A1 and surgery group A2. What have we got? We're going to have 4 rate estimates, 2 rate differences, 2 rate ratios. We'll have 4 odds estimates and 2 odds ratios. And these numbers can be computed. That's not the hard part. We can see, for example, the success rate for those receiving pretreatment 1 and were in the surgery group A1 is 100 over 1,000, or 0.1. We can see, for example, for those receiving pretreatment 2 and in surgery group A1 that the success rate estimate is 5 over 100, or 0.05, and so on. And so notice with the earlier example, so without the identification of the surgery group, we got a rate difference that was negative, a rate ratio that was less than 1, and an odds ratio that was less than 1. What do we get here? We get rate ratios that are both greater than 1, odds ratios that are both greater than 1, and quite different. Wow, lots going on here. Without the identification of the surgery group, a rate difference is negative, and the rate ratio and odds ratio are both less than 1, even though the rate ratio in the 2 surgery groups was computed to be greater than 1, and similarly with the odds ratios. And notice these odds ratios, they're different. Now we've got the estimates that come from the study that acknowledges that there were differences attributable to the surgery group that they received that is going to impact on our study of the relationship between outcome and exposure. Here, success, failure, and pretreatment group. Wow, lots going on. What is going on? And this is a summary of the information that I have just described. The 2 stratum-specific, or in this case, surgery-specific rate ratios are nearly the same, but very different from the so-called crude rate ratio that did not identify the surgery type. The surgery-specific rate differences are not even close to one another, though. See that? 0.05 compared with 0.45. Similarly, the stratum-specific odds ratios are very different. 2.1 compared with 19. So what do we got? We've got a lot going on here. First, the relationship between success rate and exposure seems to have changed direction. And in one group, that change in direction gave us 2 numbers for the 2 surgery types that were fairly close to one another, but way different from the one that didn't acknowledge the surgery type. On the other hand, for the rate difference, or the odds ratio, we got differences and odds ratios that are different in the 2 surgery groups. Oh my. So we just have fractions here. There's an illusion of simplicity, but there's a fair bit going on. We've now taken estimates of marginal probabilities, those are the left-hand fractions, and expressed them as 2 joint probabilities. Those are the 2 sets, the 2 numbers we see second. Then we can take each of those joint probabilities and express them as conditional probability times marginal probability. Now, in this case, it's a little bit trickier. We're going to have the estimate of the probability of success for those receiving surgery 1 and pretreatment 1. That is the condition then is joint. And that's going to be multiplied by the estimate of the probability of being in the surgery group 1 given the person is in pretreatment group 1, and so on. The second table I'm displaying for you here shows a curious imbalance. For example, we can see that the proportion of individuals receiving pretreatment 1 for those in surgery group 1 is 1,000 over 1,100. But for those receiving pretreatment 1 for those in surgery group 2, we can see the ratio is 100 over 1,100. Very different numbers. There's some important issues of epidemiology going on here. Before we proceed, a little bit of the technical stuff. Here then is a summary of what we've been using. In each row there, we have a marginal probability being expressed as a sum of two joint probabilities. And then each of those joint probabilities is expressed as a conditional probability times a marginal probability. But it's a little bit trickier than this, isn't it? Because in each row on the previous page, we're either conditioning on pretreatment 1 or we're conditioning on pretreatment 2. Okay. That's then a way of seeing how these numbers are established. Again, a little more of the technical here. It is now of value to interpret the estimate of the probability of success for those in pretreatment 1 as a weighted sum of two conditional probability estimates. Notice we have a weighted sum of two numbers. We have the weighted sum of 100 over 1,000 and 95 over 100, very different numbers. And the weights are different. Notice in the first case that the 100 over 1,000 gets most of the weight. 1,000 over 1,100. Okay. Now, for the same set of numbers for those receiving pretreatment 2, we again have a weighted sum of the 5 over 100 and 500 over 1,000. Notice again, those numbers are very different. And in this case, the 500 over 1,000 gets most of the weight. 1,000 over 1,100. That's going to help us to understand what's going on. Now, a little bit of context that might be appropriate here, given the circumstances here. It could be that the surgeons in this study prefer to assign pretreatment 1 to patients about to receive surgery 1. Now, this could be policy in a region or some jurisdiction, or maybe specific to the surgeons that were in the study. It's of interest to notice then that such fractions, these weights, are specific to the study, and not generalizable typically to other surgeons or other jurisdictions. This is common in epidemiology. We have some parts to this analysis that we anticipate will be generalizable to larger populations, and other numbers that we anticipate would be specific to the specific study at hand. So for this study, we have those two sets of weights. But as I mentioned just before, it could be that these two fractions might be quite different in other studies. We just don't know. So what have we got? In this context, in this way of describing things, we might prefer to see then the surgery-specific numbers as being estimates of 4 probabilities. This, as we'll see later, is a circumstance in which we believe there's no other issues that may be impacting on the success rate. Again, I don't want to overload you with too many notions just yet. But for now, we can see that the numbers that were not specific to surgery are based on the surgery-specific numbers, but then depend on the fractions that are specific to the study at hand. So, how do we go about assessing pretreatment here? Well, we've got the surgery-specific numbers, and we might anticipate that those are the things we ought to report, maybe. On the other hand, we've got that the weights don't extend other circumstances. So now let's take a look at what's going on that may help you to appreciate the circumstances we have here. A visual. I really find that sometimes visuals can be very helpful when you're trying to sort out these things. So let's give it a try. Let's then think about the estimates of the surgery-specific probabilities as being reliable estimates, but that the weights are not. They are specific to the analysis, specific to this particular study. So what we're going to do is draw 2 lines, taking those surgery-specific numbers for either T1, the pretreatment 1, or T2, pretreatment 2. We'll use a blue line for those receiving pretreatment 1, and we'll use a red line for those receiving pretreatment 2. And what do we see? Well, how about that? We get 2 lines, of course. You may find it instructive to follow where the lines go. The lines go from a weight of 0 to a weight of 1. We see that the lines have different slopes. Yes. Now, what are the actual parts to this display that come from the data at hand? Well, see if the pointer enables you to see this. We've got this number here, 0.4591, and this number here, 0.1773. The first one referring to pretreatment 1, the second one referring to pretreatment 2. Now notice 0.4591 is higher than 0.1773. That might have given us the impression that pretreatment 2 has a higher success rate than pretreatment 1. But on the other hand, this line for pretreatment 1 and this line for pretreatment 2 are possible other contexts we might have had if we had had different weights from different studies, say. So why is pretreatment 2 at least initially thought to be superior. Well, that appears to be largely attributable to the weights. Notice that we're comparing this point on the red line with this point on the blue line. On the other hand, the blue line is always above the red line. In other words, the success rates for pretreatment 1 are always better than pretreatment 2 if, for example, we were to have equal weights, say 0.5 in each, or even for any setup where we might contemplate a comparison where the weights are the same and not dramatically different. Now, in epidemiology and in biostatistics, we have new terminology that comes into play with this display, and that is the notion of counterfactuals. In this particular display, there are two numbers that are, shall we say, real, the 0.4591 and the 0.1773 are actual. Further, the endpoints of these lines at 0 and 1 are, in fact, the surgery-specific numbers. So these two endpoints and these two endpoints are the surgery-specific numbers. So what we can see is that every other point on the line is not real. Now, in some contexts, we call them counterfactual. That's another word for fiction, I guess. In some cases, some authors would argue that we could compare, for example, these two numbers, the 0.4591 and the 0.8727, because the weights are the same. So this is actual and this is counterfactual, the 0.8727. Except that if we were to argue that we could do that for this set of weights, what about the other set of weights? And we can see that in this case, we would be comparing the number actual of 0.1773 with 0.0909. Now, what I want you to draw your attention to and remind you is that these two lines have different slopes. So this difference is not the same as this number, as this difference. A counterfactual comparison here? Which one? Might we be better to just note the 4 surgery-specific probability estimates? Counterfactuals. So, a definition, a counterfactual expressing what has not happened but could, would, or might under different conditions. Okay. So many of you may have come into context with counterfactuals, and the use of the term appears in a number of different places in the epidemiology and biostatistics literature. And so the argument being that comparing observed, which are real, with counterfactual, which are not, is sometimes the basis for arguments in epidemiology and biostatistics. More on this will be established as we move forward. A little more just repeating of what I just said and for information. There are only 6 real values here. Each line has 3 real values, if you like. They are the endpoints and those with the observed weights, and all the other points on the line are considered counterfactual. Now, as I said, in some contexts, authors will argue that we should consider these vertical distances between the two lines at any common weight. But as I've noted here, this consideration, any particular one of them, is questionable as the differences between the endpoints are different. Okay. Next up in our first session in models in epidemiology and biostatistics is a discussion of the various measures we have that are used in epidemiology and biostatistics. We will see that it is crucial for the investigator to establish certain things in advance of analysis. Otherwise, you're going to face some of the issues that we're going to see over and over again throughout our establishment of this material. Now, first of all, we can note that the risk difference is merely the negative of the success rate difference, and that the odds of failure ratio is simply the reciprocal of the odds of the success ratio. That means if one is analyzing the data with a rate difference, it doesn't matter whether you formulate things in terms of the probability of success or the probability of failure. Your analysis will be the same. In the case of the failure rate and the success rate, it's simply a sign change. And in the case of the odds ratio, it is simply taking one reciprocal or another. Now we come to the first ouch, and that is that the risk ratio or the failure rate ratio is not a simple function of the success rate ratio. Ouch. It means that you need to formulate in advance whether you wish to study a failure rate ratio or a success rate ratio, because your analysis will be different. Uh-oh. Another uh-oh, right? Now, here is some of the analysis here. I don't propose to spend too much time with this. We can go through some of the calculations. They are fairly elementary. This is merely showing that the success rate difference is the negative of the failure rate difference. And then this little bit of algebra is showing that the odds ratio in terms of failure is the reciprocal of the odds ratio in terms of success. Very simple. Unfortunately, we do not have this nice simple relationship with the two rate ratios. In fact, a fairly elaborate set. For example, the rate ratio in terms of failure is the odds ratio in terms of failure times the rate ratio in terms of success. In other words, one rate ratio is not computable from the other. Ouch. So here's a little summary of what we have. If we interchange those exposed and those not exposed, simple things happen. But if we interchange case control status, in other words, here changing success to failure or vice versa, we get a sign change and a reciprocal for the risk difference and the odds ratio, but for the risk ratio, well, it's not easy. So we can see that an interpretation of results can depend on the measure to be used in assessing an intervention. Rate differences can offer very different interpretations from rate ratios, and so on. What we'll see as we move forward is that the crucial concepts of modification and confounding are both functions of the measure we use to establish an association. Uh-oh. In other words, if we wish to discuss modification, we need to specify the measure of association. Similarly, if we are in a position to assess confounding, one must establish which measure of association is being used. Both of these issues are, frankly, very confused in the health research literature, and it is a big, shall we say, wake up that you need to be careful about moving forward. Okay. Based on the simple analysis, we might have concluded with this study that the success rate could be improved if one received treatment too. But now we have, in fact, seen that if we were to identify the surgery, we get the opposite. We see that surgery type advises us or clarifies for us that in fact it is pretreatment 1 that has the higher success rate. There's a lot of language here, and we'll be investing quite a bit of time in all of them. Here, the stratified analysis, the one with 2-by-2 tables, has enabled what is sometimes called a salvage job. Many authors have used this term. It's hardly original. Notice then that a number of choices need to be made, and in principle for your work, you need to make such choices in advance of doing analysis, not afterwards. Otherwise, you face this tremendous quandary. Which set of results do we report? Now let's look at how this would have been seen using Stata. Here, CS here is the command one uses if one wishes to obtain either the risk difference or the risk ratio here. These numbers we saw very early in this session. We then obtain a test of significance for association here. This is the approximate chi-square test based on this 2-by-2 table. We will also notice that this number that Stata reports looks like it's 0. That's not possible. We would correctly report here that the probability is less than some number, like less than 1%. Tests of significance cannot have p-values that are completely 0, that are exactly 0. So you have to be careful there. We also get confidence limits for the risk difference and the risk ratio. Just to keep in mind, this number, minus 0.28, is the estimate of the risk difference, and these are confidence limits for the actual risk difference in the probability domain, in the population domain. Similarly, for the risk ratio, this is the estimate of the risk ratio. We would label this with hats. We would say RR with a hat over it. And here are confidence limits for the actual RR. Okay. If we were to repeat this analysis for the risk difference in terms of failure, the rate differences merely change sign in the case of the risk difference, but notice we get a very different statement of the risk ratio. We get this number 1.52, which does not have a simple relationship with the number 0.386. Uh-oh. So the estimate and the confidence limits here are for the risk ratio, or, if you like, the failure rate ratio, whereas here, this number labeled risk ratio is actually the success rate ratio, as we noted earlier. Okay. Here is then a little bit of a summary of what was in those displays. Not too surprising, and a nice reminder of things. In this instance, the tables contain quite large numbers, And so the difference between the approximate test and the exact test will be inconsequential. But you may want to try this from time to time as you're gaining some experience with this. Here then is the same set of results for the odds ratio. This number, 0.253, the estimate of the odds ratio, or OR with a hat over it, and the confidence limits for the actual odds ratio in the population domain. The ratio, the odds ratio in terms of failure is merely the reciprocal, and you can check this. This number is the reciprocal of this number. And these two numbers are reciprocals of one another. Very simple. And there's a simple set of summary of this information for you. Alas, the rate ratio in terms of failure is not the reciprocal of the rate ratio in terms of success. Care needs to be taken here. These numbers are not the same. Now we come to the stratified analysis. First of all, for the, in this case, the success rate ratio. What do we see? The success rate ratio estimates of 2 and 1.9. Aha, we saw those earlier. And we then would say, okay, these two numbers are very close to one another, right? And very different from the crude. Since these two numbers are very close to one another, we would then see in epidemiology the reporting of the so-called Mantel-Hansel, that M-H from Mantel-Hansel, estimate of the assumed common success rate ratio. And we can see that these two numbers, the crude and the adjusted here, are very different. Further, we get a test of significance for a difference between these two surgery-specific success rate ratios. And we can see there is no evidence of a difference between the success rate ratio in surgery group 1 and the success rate ratio in surgery group 2, this p-value being very high. Now we come again to the tricky piece here, and that is that the analysis done in terms of the failure rate ratio gives us very different information. Now we get that these two estimates are very different. And the test of significance for the assumption that the two failure rate risk ratios are the same is discredited. This p-value is very low. In this instance, we would argue that we should not be attempting to combine these two numbers, right? This Mantel-Hansel combined is essentially a weighted average of the number 0.94 and 0.1. And this number 0.655 refers to no one. It doesn't refer to people in surgery group 1, and it doesn't refer to people in surgery group 2. So the actual computation here is discredited. It's displayed by Stata, and even confidence limits are given, but this number is meaningless. So the success rate ratios and failure rate ratios are very different. And this is a summary of that information. Okay. And as I'm repeating here, the number 1.909 might be the reportable number. It is an estimate of an adjusted or assumed common odds ratio, or risk ratio, excuse me. Well, Gordon, what is it? 1.909 is an estimate of the assumed common success rate ratio. Right. But the number 0.6552 refers to no one. It is, in fact, a weighted average of two failure rate ratios that are obviously different and are seen to be different with a test of significance. On the other hand, if we consider the analysis done by an odds ratio analysis, we get the two numbers here, very different. The test of significance clearly showing us that the two odds ratio estimates appear to be estimating different things. Right? So there is an identification here of modification. And we'll be coming back to all of these notions in future sessions. And no meaningful discussion of confounding is appropriate here. Rather, we need to note that these two numbers are very different. The reciprocal analysis essentially is the same. All of these numbers are reciprocals of the numbers in here. So that's fine. And we see that. The odds ratio analyses yield the same results. Okay, we have one more issue for this particular session I want to spend just a little bit of time with. And that is, we now have the ability to assess these counterfactual arguments, not just for the rate differences, but for rate ratios and odds ratios. There's a fair bit going on here, and I'll be referring to these displays in other sessions. But for now, what we can note is that you can download the ADO, counterplot.ado, and place it in the personal ADO directory. A little bit of technical stuff here if you've not done that before. So here is some of the technical information you may need in order to use the counterplot script that is included. And in doing so, then, one can then compute or input for example, the cold flush data that we've used throughout this session, and consider a variety of different displays. Here's the one that we had initially. An assessment of the rate difference in terms of success with the two lines. Okay. Pretreatment 2 below pretreatment 1. But the two lines with clearly very different slopes. Hence, the difference between the endpoints are different, and any comparison between the blue and the red is different. The actuals are displayed here for you as well. On the other hand, if we were to look at an analysis of the success rate ratio, we see we get almost parallel curves, nearly parallel curves, and an argument that this comparison here, very close to this comparison here, for example, as we saw before. And this display of these parallel curves provides us with a descriptive way of seeing that if we were to decide to use the success rate ratio for our report, we may wish to report that there is evidence of confounding, and that it will be meaningful to report the success rate ratio adjusted for surgery type. Okay. Here are then the other displays. Here is the rate difference display in terms of failure. It's merely the sign change that was noted earlier. Here is the risk ratio or the rate ratio in terms of failure, and the result is very different from the rate ratio in terms of success. Here we see this difference is big, right? Very big difference, and here it's a tiny difference with the two weights. Fair bit going on here, but I hope the visuals do help you to understand what's in play here. Similarly, we can look at the logarithm of the odds ratio. The reason for displaying it in terms of logarithms will become clear later on in these sessions. But again, we are seeing a difference with one set of weights being different from the difference with another set of weights. Oh my. And we get exactly the same analysis again in terms of reciprocals. Here, the odds ratio in terms of failure. That this difference here with one set of weights, very different from this difference with the other set of weights. Okay, one more point for you, and that is that we may wish, when you're preparing your work, to paste your Stata output into a word processor, and I highly recommend you use a fixed font, fixed spacing font. Sort of old-fashioned, you might be thinking. Oh, Courier, that's an old thing. But for the setting up of the tables and for most of the pages, using a Courier font, I would say 9-point and bold, gives the clearest images. I have found from a whole lot of exploration here that when you import your images into your word processor, the clearest visuals and maybe the best choice is the so-called PNG format. Okay, and there's a bit more there. The suffix of GPH is specific to Stata, and you can save your images within Stata in that format and then return to them at some later date.